Hello there. Today's topic, I'll be talking about electronic defects and dislocation. Before I talk more about electronic defects or material defects, let's think about what's material defects. Defects, by definition, any deviation from the perfectly ordered, arranged constitutes is called defect or imperfection. Well, this defect sometimes are called thermodynamic defects because the number of these defects depend on the temperature. Here, I'll focus on two kinds of defects. One is electronic defects, like oxygen vacancy and its electronic defects. The other is dislocation, such as screw dislocation, edge dislocation, and threading dislocation. As I mentioned, defects are related to thermodynamics and thermal energy. Let's deep dive in thermodynamics first. Well, thermodynamics. What's thermodynamics? Thermodynamics is a branch of physics concerned with heat and temperature, and their relation to energy and work. It defines macroscopic variables such as internal energy, entropy, and pressure. We need to know thermodynamics is something related to energy, entropy, pressure. Let's think about material oxidation. Now, if we want to elaborate thermodynamics more, material oxidation is one of the most common reactions which can be described by thermodynamics. Material oxidation is the reaction between material and oxygen pressure. Here it is. The formula is plus O2 equals MO2. When we think about material oxidation, we need to think about thermodynamics. When we think about thermodynamics, we need to think about thermal energy. Without thermal energy, there is no reaction. The interaction between material and oxygen pressure happens when the thermal is included in the system. Therefore, you can see the equation here. Delta G equals minus RT natural log K equals RT oxygen pressure. The energy form, like delta G temperature T and oxygen pressure P, are included in the formula. Okay? We can further plug given free energy versus temperature here to compare each material oxidation capability. This is so-called oxygen affinity. From the right side, we can see the material studied here. All their energy is lower at lower temperature compared to higher temperature. The material with lowest energy here among all materials is lengthen. In contrast, here lengthen. In contrast, the material with the higher energy here among all materials is tungsten. This means lengthen is a material which likes oxygen most. Therefore, its metal oxide form is observed at lowest energy. However, tungsten is the material which dislikes oxygen most. Therefore, higher energy is demanded to form tungsten oxide material. Well, electronegativity, we also need to consider about electron negativity. Then the understanding of material interaction, then we can relate it to the point defect, the oxygen vacancy. Electronegativity, by definition, is the determination of atoms which capability to lose or gain electron. For example, we know hydrogen here. Hydrogen is preferred to donate electron to bond other elements. In contrast, fluorine here is a material which electron configuration is almost fully occupied. Fluorine just needs one additional electron, then its electron configuration is perfect. Fluorine is willing to accept electron from others. Yeah, this is the idea of electronegativity. From the diagram shown below, we can see fluorine is a relatively high value here. However, hydrogen is at a relatively low value. According to Pauling electronegativity, here the equation here, Xa and Sb, the electronegativity, the function of bonding length and energy in between AA, AB, and BB. Well, let's further dive into very interesting case. As I mentioned before, hydrogen is only occupied by one electron. Hydrogen is therefore easy to lose electron. In contrast, chlorine has 7 electrons. 7 electrons at the outer layer. Therefore, chlorine is willing to accept 1 electron and make a perfect configuration. You can see the electron cloud of hydrogen is smaller than the one of chlorine. Because hydrogen is 1 electron lost and chlorine is 1 electron gain, the unequal size of the electron clouds can be found. Okay, amazingly, hydrogen bound together, the electron clouds of each size are equal. Since hydrogen are belonging to the same family, they share electrons. The electron clouds at each size are equivalent. Well, yeah, here's the idea of hydrogen chloride. When they bond together, the electron clouds will look like this. So, okay. Oh, yeah. Let's think about the material defect again. Material defect here we study point defects 0 dimension, and the linear defects 1 dimension, and the interfacial defects in 2 dimension, and volume defects. So for point defect we have vacancy and interstitial. The dimension is 0 dimension. And for linear defect, we have age and skew dislocation, and also dislocation, and the missing line or additional line, electron line. So it is 1 dimension. And for interstitial defects, or interfacial defect could be grain boundary or external surface. It is 2-dimensional defects. And the volume defect, like voice and bulk defect, it is 3-dimensional defect. So, well, vacancy is a very interesting topic. Vacancy. Okay, let's deep dive in 0-dimension defect vacancy. What is vacancy? Yeah, vacancy is nothing. Nothing is there. We call it vacancy. The equilibrium number of vacancy NV is the ratio of the total numbers times the activation energy QV and Boltzmann constant K and the absolute temperature T. Here is the equation to describe the vacancy. And N is the total number of atomic sites, and the QV is the energy required for the formation of a vacancy. Here you can see the diagram here. The perfect structure will look like this. When this element is gone and will leave the side here, empty side here, and it is a vacancy. Therefore, for physical defects, point defect, we have vacancy, unoccupied lattice site, substitutional impurity, occupied normal lattice site, and the interstitial impurity occupies a position between lattice sites. That's it. Well, when we think about the point defect, we need to think about very famous case here. It is the Frankel disorder and Schottky disorder. You can see the diagram here. Frankel disorder or Frankel defects, it consists in the displacement of an atom from its lattice position to an interstitial site, and from the lattice position to the interstitial site, and creating the vacancy at the original site and the interstitial defects. 2M they move into the interstitial site and leave the vacancy here. It is called Frankel defects. So what is a Schottky defect or Schottky disorder? It happens in ionic crystal like X and M, the AB, equal number of Ki and Ni's. Okay, even they're missing the equal number of Ki's and Mi's. This is so-called the shock defect, and also keep the electrical neutrality. Well, so we have the background for the point defect, the thermodynamics, and then we can further dive in the oxygen vacancy after we understand the oxidation reaction, the material interaction. So let's deep dive in oxygen vacancy here. Oxygen model, oxygen vacancy, basically we study the oxygen vacancy. Oxygen vacancy can be described by this equation. So for the oxygen occupied at the oxygen site, we can describe the OO here. And when the oxygen is gone, it left the oxygen vacancy there. Here is an example, oxygen is gone. Oxygen vacancy here, the vacancy site is generated. And because this oxygen has no 2 electrons outside, so also we release 2 free electrons. And you can see the vacancy generation and the 2 electrons, free electrons are also created. And for more of oxygen, more oxygen from oxygen to the free oxygen here. So this is the equation to describe this behavior. Okay, basically, let's think about the oxygen vacancy and the thermodynamic reaction. For example, we use the hafnium dioxide and oxygen vacancy interaction. Basically, it is a reduction reaction, and also it is related to the oxygen pressure and gives free energy. We need to keep the neutrality conditions, so the charge balance here, and combining the equation from 1 to 3, we can get the equivalent oxygen vacancy is correlated to the oxygen pressure and gives free energy and the temperature T. And associate this with the diffusion coefficient function D0. And finally, we can determine the diffusion coefficient of oxygen vacancy and the pressure, temperature, and the Gibbs energy, the relation. So basically, oxygen vacancy model, we can base on the thermodynamics and the oxidation reaction, and just think about the electron negativity behavior, and then we can conclude and to systematic estimate the oxygen vacancy the concentration for a material.